Hello, chemistry students. In this video, I'm going to be showing you how to balance a double replacement reaction. So a double replacement reaction, sometimes called a double displacement reaction, occurs when two ionic compounds split and trade partners. The compounds that are formed will be based on the charges of the ions. So the general format here, we have AB, which is a cation and an anion, and then CD, which is another cation and anion. We have two ionic compounds, and they're going to trade partners. In this case, you can see here that these arrows are showing that the cation that is with this anion is going to switch places, and the opposite cations and anions are going to trade partners. So we end up with CB and AD. And it's important that you do it in this way that because A and C are not going to combine and B and D are not going to combine because they have the same type of charge. A positive ion is going to need a negative counterpart. So that's why we have A with the D and C with the B. So let's look at an example of this. Say we were asked to predict the products and balance the chemical equation for a reaction between barium chloride and potassium phosphate. Now, this is all that we're given. So we're going to need to figure out what kind of compounds are going to form as a result of the combination between these two, what their formulas are going to be, and then that's going to cause us to have to balance the chemical equation if it's not balanced already. Some equations end up being balanced already. But let's go through the steps here. So first, let's look at our compounds. So based off of the name, we have barium chloride. That's going to be a barium ion, which is 2 plus, based off its position on the periodic table. And chloride is going to be 1 minus, based off its position, which means that we're going to need 2 chlorides to balance 1 barium. So we're going to get the formula BaCl2. For magnesium or potassium phosphate, that's a typo. For potassium phosphate, potassium is a 1 plus charge, and phosphate, that's one of our polyatomic ions. And if we look at our chart, we see that it has a formula of PO4 3 minus. So since we have a 3 minus charge here and a 1 plus charge here, I'm going to need 3 of this ion to balance out the phosphate. So the compound is going to be K3PO4. All right, so we can start writing our chemical equation because since we know the reactants, so we have BaCl2 plus K3PO4 becomes something. So we need to figure out what's going to be on the right-hand side of the equation. But since we know how a double replacement reaction works, we know that the cations and the anions are going to switch partners. So we can assume that from a barium chloride and potassium phosphate reaction, that we're going to end up with potassium chloride and barium phosphate. The cations and the anions are going to switch places. So let's figure out what the formulas of those resulting compounds will look like. So potassium chloride, we know that potassium has a +1 charge and chloride has a -1 charge. So they're going to come together 1 to 1. So we'll have KCl. For barium phosphate, it's going to be a little bit more complicated. Barium is a 2 plus charge and phosphate is a 3 minus charge. So we're going to need to do the thing where we make a common multiple, in this case 6. So we're going to need 3 2 pluses to get 6 plus, and then we're going to need 2 3 minuses to get 6 minus. So we're going to end up with the total formula of Ba3PO4 2. Now we can put it all together since we know the identities of our products. So we have BaCl2 plus K3PO4 yielding KCl and Ba3PO4 2. Now we have a chemical equation here, but in order for it to obey the conservation of mass, we need to make sure that it is a balanced chemical equation. So is this balanced? Well, let's make a table and find out. On the reactant side, we have 1 barium, but on the product side, we have 3. On the chloride side, we have 2 chlorides, and on the product side, we have 1. On the potassium side, we have the reactant side, we have 3 potassiums, and on the product side, we have 1. And for phosphates, we have 1 on the reactants and 2 on the products. So from this, we can intuit that this is not balanced at all. So this is not going to be an acceptable final chemical equation. We're going to need to figure out what the ratios of all of these things are in order to obey the law of conservation of mass. So what we can do is we can start adding coefficients. Remember that you can't do anything to the formulas themselves. These are going to be how these always form. Barium and chloride are always going to have a 1 to 2 ratio. So I can't just add like a 3 here to make us have 3 bariums because then that's not going to be a balanced ionic compound. All we can do is change the ratio in which the different substances are going to combine and what the ratio in which they're going to form. And the way we can do that is by adding coefficients to the equation. So Sometimes this is sort of a guess and check process, but it helps sometimes to start with one of the substances and start adding coefficients and see how that changes everything. And it's kind of like solving a puzzle. You need to move the pieces around until they all fit into place. Also, you'll notice on this table that I've kept phosphate as PO43 minus rather than splitting it up into phosphorus and oxygen. And that's a useful thing to do with polyatomic ions when you're balancing an equation, because the polyatomic ion is going to be retained. It's always the P's and the O's are always going to be stuck together and they're not going to separate. So we can treat it like one unit. So let's start by adding a 3 here. We need 3 bariums on the reactant side to match the 3 bariums on the product side. So I added a coefficient of 3 in front of barium chloride, and that'll give us the 3 bariums that we need. However, chloride is also attached to this, so the 3 is going to affect it as well. So we went from having 2 chlorides to now having 6 because we have 3 times 2. So we've managed to balance our bariums, but our chlorides are not balanced, and neither are our potassium and our phosphate. So we're going to need to add some more coefficients to this. Um, I think a useful one to do here is going to be the phosphate, since we have 2 of them here, and that we might need to change other stuff in a different order. Sometimes you need to guess and check which one to do next, but I'm intuiting that I should change the phosphate next. So I added a 2 here so that I could match the 2 phosphates on the product side. So that balances that, but since the potassium is also connected to it, that also changes that. So then we have 2 times 3 times the potassium, and now we have 6 potassiums on this side. So now the barium is balanced and the phosphate is balanced, but the potassium and the chloride are still unbalanced. So we're not done yet. Now I'm going to add a coefficient to the product side. I'm going to add a 6 in front of the KCl since I know that I need 6 of both of them. And that changes our potassium on our product side to 6 and our chloride to 6. And let's see here, 3, 3, 6, 6, 6, 6, 2, 2. Now we are all balanced. So that tells us that our final balanced chemical equation for the reaction between barium chloride and potassium phosphate is going to be 3 barium chlorides reacting with 2 potassium phosphates to produce 6 potassium chlorides and 1 barium phosphate. All right, and I hope that helped.